All right, so last time I introduced the structure of chlorophyll and the difference between chlorophyll A and chlorophyll B. There's a very slight structural difference between the two, and both are functioning in plants during photosynthesis. So there was a very, very famous experiment carried out by a guy named Theodor Engelmann in 1883. So notice in our study of the history of the discovery of the components and functioning of photosynthesis, we've spanned about 200 years. What he did was this experiment which looked at the rate of photosynthesis, or measured the rate of photosynthesis along the visible spectrum. So this measurement here is from 400 nanometers to 700 nanometers is the visible spectrum, from the violet end to the red end. And this is an example of why I like to remember not Roy G. Biv, but Vib G. Yor, because from left to right, it starts at violet. Vib G. Yor from left to right. And that helps me remember which end of the spectrum has low wavelengths or short wavelengths, and which end has long wavelengths. So what Engelmann did was a very elegant experiment. And this describes the experiment. I'm not going to read it to you. You can read it for yourself. I'm just going to describe it here from the diagram. So, as the diagram shows, this is a microscope slide, and you may not have that label on yours. I just added it recently. But the whole thing here represents a microscope slide. And so on this microscope slide, Engelmann laid out a filamentous algae. So this is a filament of algae. Notice there's a cell, 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 cell. Remember, filamentous algae are a chain of cells. And along that filament of algae, he added obligate aerobic bacteria. And if you'll recall, obligate means they have to, and aerobic refers to oxygen. So this is bacteria that has to have oxygen. And not only is it obligate aerobic bacteria, but it was also motile. In other words, if you'll recall, the structure that bacteria can have for locomotion, for moving around, for swimming around, is flagella. So, of course, this would be under water. So there would be water on the slide, and because the algae requires water, and the bacteria would then be able to swim to where they wanted to go. And that's a crucial component of what he did here and what he was thinking and trying to figure out which wavelengths of light were absorbed by the algae for photosynthesis. Once he had that set up, he used a prism to break up white light, the full spectrum of the visible spectrum, into the colors. And he focused that rainbow of colors, the product of the prism, across the microscope slide, so that there was violet at one end and there was red at the other end. So the full visible spectrum was divided up by color across the slide according to wavelength. And then he just waited until the bacteria swam to where they preferred to go. And because they're obligate aerobic bacteria, they swam towards where there was the most oxygen. Where there was the most oxygen is where the most photosynthesis was going on. So there was a lot of oxygen being produced at the violet-blue end of the spectrum. There was a lot of oxygen being produced at the red end of the spectrum, but there was relatively little oxygen being produced, or low oxygen concentration, at the middle of the spectrum, in other words, in the green-yellow part of the spectrum. So by looking at the distribution of bacteria along the filament of algae, he was able to infer where more photosynthesis was going on and where less photosynthesis was going on according to wavelength, or along the wavelengths of the visible spectrum. So he concluded that the algae absorbed primarily wavelengths at the blue-violet end and the orange-red end of the spectrum, but not so much in the green middle part of the spectrum, which, of course, as we know, is reflected, and that's why plants are green. So basically what Engelmann demonstrated and what Engelmann produced was what we would refer to as kind of a living action spectrum. Notice that, oops, I just messed up. The action spectrum of photosynthesis, right? This is an action spectrum. It represents an action spectrum anyway. What an action spectrum really is a graph. But a graph of the action spectrum of photosynthesis looks very similar to the tracing here that shows where there's more bacteria and where there's less bacteria, right? So this kind of looks like a tracing on a graph, a line on a graph, right? So this is kind of a living graph. And if we were to place a y-axis here, a y-axis scale here that represents the rate of photosynthesis, that's basically a graph. So, but in Engelmann's case, that's a living graph, a living action spectrum of photosynthesis. Something that would be considered a real action spectrum would be an actual graph that would plot the rate of photosynthesis along the visible spectrum. And that's what we're looking at on this slide. But this isn't an action spectrum. This is what's known as an absorption spectrum. And an absorption spectrum shows the absorption of one particular molecule or one particular pigment. So you'll notice we have absorption spectrum tracings here for both chlorophyll A and chlorophyll B. But because they're shown separately, this is known as an absorption spectrum. In an action spectrum, what you see is the combined effect of both of them together. And if you combine these together, you see that it matches very closely Engelmann's action spectrum, living action spectrum. So what this graph does is plots the absorption the absorption percentage against wavelength for both chlorophyll A and chlorophyll B. So this is an absorption spectrum, and it shows the absorption of individual pigments. That's the difference. We're seeing the absorption of individual pigments, and we can see the difference between the absorption of chlorophyll A and chlorophyll B from this comparative absorption spectrum, rather than the action of all the pigments combined during photosynthesis, as in the action spectrum that Engelmann demonstrated. And as we can see from this, both chlorophylls, although slightly different, absorb the most light energy at the blue-violet ends of the visible spectrum and the red end of the visible spectrum, just like was demonstrated in the action spectrum from Engelmann. And the middle part of the spectrum, the green-yellow part of the spectrum, is reflected, and that's why plants are green. So to emphasize that point, wavelengths that are not absorbed are reflected. And most photosynthetic organisms are green because chlorophyll reflects the green wavelengths of the visible spectrum. But as you know, there are accessory pigments that are not green that also function in helping to absorb different wavelengths for photosynthesis. So for example, the algae, like there are red algae and brown algae and golden algae, as we learned in the last unit. And even in plants, when the leaves turn colors in the fall, those accessory pigments are showing through because the chlorophyll goes away. So this shows the wavelengths that chlorophyll absorbs, and we know that what it's absorbing is energy. I mean, if you walk outside in the summertime with the sun blaring on with a black shirt, you know very well that you are absorbing energy. That black shirt absorbs more energy than, for example, a white shirt, which would reflect it. So the chlorophyll is absorbing energy here, but what is it doing with that energy? What happens to the energy when chlorophyll absorbs it? That's what we're going to look at next. So here we're looking at a diagram of an isolated chlorophyll molecule. And so this is just one molecule of chlorophyll, and we're looking at what happens to that molecule when light energy strikes it. And you'll notice here that the light energy is labeled as a photon. A photon, as you know, light travels in waves, and that's why we have been talking about wavelength. But the other property of light is that it has these packets of energy that are known as photons. So light behaves as both a particle photons are the particles, and a wave. And I know that's kind of hard to wrap your head around, but you just need to accept it at this point, and you'll study that more when you take physics, for example. But the chlorophyll here is absorbing that energy. So any compound that absorbs light absorbs energy from that light. So chlorophyll, that's its function, is to absorb energy, light energy. So this describes what's going on, and I'm just going to read through it with you and refer to the diagram as we go through it. So when chlorophyll absorbs a photon of light, that's what we're seeing here, an electron is excited. Remember, electron, that's the symbol for electron, a lowercase e with a superscript minus, because electrons are negatively charged. So the electron is excited to a higher energy level, as we say, or an excited state, as they have labeled in the diagram. Remember, the electrons orbit the nucleus in atoms at different energy levels. So that's basically what we're talking about here. And if the electron has nowhere else to go, as in this case, because this is an isolated molecule of chlorophyll. So this is a molecule all by itself, and when the electron gets excited, it has no place to go. But in photosynthesis, it does have a place to go. So it's not going to fall back to its ground state, as we say. But because this is an isolated chlorophyll molecule, that electron has nowhere to go, and eventually will fall back down to its ground state. So you can think of it as kind of having potential energy. It's been excited to a higher energy state. It has potential energy, and that potential energy will be released when it falls back down to its ground state, which is more stable for it. That's the reason it would fall back down to its ground state. And so it releases energy in the process, releasing energy in the form of heat and a photon. Notice heat and a photon. And this light, the photon is light. This light is going to have less energy than the light that came in, because some of that energy is lost as heat, right? So the energy is being released as both heat and light, but that light's going to have less energy. That means a longer wavelength. That means it's going to tend towards the red end of the spectrum. And that's what we see, that the light that is released from chlorophyll after it has absorbed light energy and the electron falls back down to its ground state, that light that it releases is going to be at the red end of the spectrum, 683 nanometers to be exact. I looked it up. And that's red, and that's known as fluorescence. When a molecule or something gives off light, that's known as fluorescence. And so this is the fluorescence of chlorophyll when it's isolated from the photosynthetic, the rest of the photosynthetic system. So this is a solution of chlorophyll, and you'll notice that it's red. And that's because of the red fluorescence. It's fluorescing red. So this solution was exposed to light, therefore it absorbed energy and excited the electrons in the chlorophyll, and then it was placed in the dark, and that's why it's fluorescing red. Now it's in the dark and it's fluorescing red light, the red wavelengths of light. So this is just a curious behavior of isolated chlorophyll, but it shows how chlorophyll is able to absorb energy and release energy. And these electrons are what's important in photosynthesis, because, as I already mentioned, photosynthesis is electric. So what's important is where the excited electrons go during photosynthesis, right? So that's what we're going to look at next.